So we've talked about how to find the potential, electrical potential in a uniform field, which means we can now find how much energy for every single unit of charge we move in a field we get, okay? It depends on the field strength, and it depends on the distance you move the particle in that field. Or conversely, if you're just given the potential difference from one point to another, that just tells you how much energy you gain for every single charge you move. But it'd be nice to know how to find the electrical potential for any distribution of charge. We only right now know how to do it for a uniform field, so something between two infinite charged plates. And you don't find a lot of those infinite charged plates around, as it turns out. Well, the atomic unit of finding a distribution of charge is always going to be a single isolated charge, which I'm going to call capital Q. We've done this before for the electrical force, the Coulombic force, if you like, on some test particle at some point in space. That was the Coulomb law. And then we used the Coulomb law to figure out what the electrical field had to be there. They're, of course, very close related. Now we're going to go ahead and turn that around and find the electrical potential. Okay, well, there's two things you need to ask. What's the formula, and where is the 0 point? I'm going to start by giving you the formula. This looks very familiar to what we did with gravity. It's K capital Q over R. You notice this looks a lot like the Coulomb law, except, of course, we only have one Q in here, and it's only R to the first power in the denominator, not R squared. We had the same thing with gravitational potential energy before. What's going on for people who have had calculus or are vaguely aware of what calculus says, this is the integral of the force. That is actually a very general rule. I'm not going to prove that this works. You can convince yourself if you like that this gives you the right units. I am going to say, however, the second point, where is the 0? The 0 is way off at infinity, okay? In any direction. It doesn't matter where you go. The potential will be 0 at infinity everywhere, okay? We did this with gravity again. We imagined how much energy a gravitating particle would gain by coming from infinity down to some point, in this case, some distance r from the center of the charge. Or charge, it was center of the mass before, it's center of charge now, of course. It's the same thing here. In practice, you never come from infinity, although frequently you come from almost far enough away. An electron coming in and getting caught by some atom, if you're coming from more than, maybe a few nanometers away, it's basically infinity for these purposes, for example, and you really don't need to include any correction on that. Okay? That is the potential. With this potential, you can, it turns out, find the potential of any set of charges, because all charges are made up of a collection of positive and negative point charges, no matter how you distribute them. Okay? We're not going to do that in this class because it gets complicated and annoying. Okay? But you could, and that's what's important. Okay? And if you can do that, you know how much energy per charge is associated with a given position. It's kind of like the equivalent of a height. Okay, I'm going to leave off there, and I'm going to come back and talk about equipotentials in a later video.